4 and 5D elements, looking at general picture at what happens below 3D. So this is our 3D elements we already look at, and this will be group of 4 and 5D transition metals. 4D will have 5s2 4DN configuration, with usual exception for chromium, molybdenum, and tungsten. And 5D will have full 4F14 subshell, making extra 14 protons and 14 electrons makes these atoms smaller than they should be. That's why size of atoms in period 5 and period 6 is approximately the same, and properties of these elements are more similar than you would expect. Total number of electrons on outer shell is equal in this case to the number of the group. So group number 4 electrons, and largest oxidation number is 4. Group number 5 electrons, highest oxidation number +5. Group number 6 electrons, and highest oxidation number is +6. Group number 7 electrons, and highest oxidation number is +7. Group number 8 is 8 electrons, and highest oxidation number for ruthenium and osmium is +8. Recall that iron cannot get there. Now there are 9 and 10 outer electrons for rhodium, iridium, and palladium and platinum. We do not have these oxidation numbers, but what does it mean? That when you remove, say, 6 electrons from platinum, the remaining number is still 4, and they participate in chemical bonding. That's why you have plenty of electrons for covalent bonding, and most of compounds of these elements are covalent or have large covalent component in bonding. So now let's look at first 8 elements in this group. In this case, highest oxidation number is the number of the group, but it does not mean that other oxidation numbers do not exist. Exactly the same as it was for 3D. Now, one more important difference is that you can have a bond between two d transition metals. So d orbitals can make bond between themselves. This was very unusual situation for 3D, however it exists. In case of 4D and 5D elements, it's rather more common. So what is the possibility? You may have z-square orbitals making sigma bonds between them. There is lobe from one metal, lobe from another metal, and they make sigma bonds as usual. Now, it is possible to make pi bonds like this and this, or perpendicular direction, this and this. They are not exactly the same as pi bonds for p orbitals, because p orbitals will be staying on axis, and here is larger overlapping because because they are directed towards each other. So we have very strong sigma bond here. We have 2 pi bonds. But now we have chance to have one more type of bond, which would be delta, characteristic to d orbitals. When 2 orbitals are parallel to each other and still negative, negative, positive, positive lobes will overlap. This overlap is not as large as for pi or sigma, still it is detectable. So in this case, these 2 atoms make quadruple bond. That was impossible for sigma and p orbitals only. Historically, the first compound in which it was detected, it was the rhenium complex Re2Cl8 2-, where very short distance between 2 rhenium atoms was detected in a crystal structure. Here we can say that we have sigma 2 pi 4 delta 2 bonding, which means 1 sigma bond, 2 pi bonds, and 1 delta bond, as it was described in a previous example. There are plenty of such compounds in 4 and 5D groups. It does not mean that metal-metal bond does not exist for 3D. Just an example of chromium acetate, chromium, and this is acetate groups and 2 waters above and below with visible metal-metal bond. Same, very similar structure is for copper acetate and so on. But delta bonding is not prominent there, and the description was possible without making delta bond. So now let's look at specific elements. Zirconium. Main compounds are zirconium dioxide, which in nature has always impurity around several % of hafnium dioxide. Properties of these 2 would be very similar in most cases, other than nuclear energy applications. Zirconium dioxide can be made fantastically beautiful jewelry because of very high refractive index, close to diamond. But more interesting, its use for ceramics. Its melting point is above 2700 Celsius, which makes it very attractive for high temperature application, making ceramic tools, making grinding bowls, and so on. Zirconium can be converted to chloride and then reduced to magnesium to make zirconium metal, exactly the same as titanium. Same is true for hafnium. For nuclear energy application, it is very important to have zirconium free from hafnium. So there is special, very complicated separation procedure. Zirconia, zirconium dioxide, should not be mistaken with zircon, bright red zirconium silicate, which actually was known for millennia and gave name to the element itself. Niobium and tantalum have highest oxidation number of 5. Contrary to vanadium, reducing niobium and tantalum is rather difficult. There is some analogy between niobium and antimony, so group number 5 and group number 15 You have niobium pentoxide for large area, and then in very basic you have niobates. For antimony you have these in acidic area, but coordination numbers are similar. Same for tantalum. Tantalum pentoxide and bismuth pentoxide are insoluble in water for most of area of solutions. Tantalates are possible, but you are not making them from water. What's important to remember that bismuth does not want to be +5. It prefers oxidation number +3, while tantalum prefers +5. Molybdenum and tungsten have some differences in their behavior in aqueous solutions. In very basic, both of them make molybdate and tungstenate ions. In acidic area, they are polymeric anions for both of them. But in very acidic area, tungsten makes solid tungsten trioxide, when molybdenum can make the same and then dissolve, make cationic species, still soluble in water. Very interesting feature for both of them is making complex polymers with phosphorus, silicon, and other elements of groups 4 and 5. In this case, you see phosphate reacts with 12 molybdate ions in acidic medium, so actually we are talking about isopolymolybdates in this case. The whole assembly has phosphorus in the center, 12 molybdenum atoms, and 40 oxygen atoms, and has charge 3-. Because it's very large, it can be easily precipitated with largely sized cations like ammonium, so NH4 3 PMO12 O40. It's possible to replace molybdenum by vanadium or several other elements in 1 or 2 positions. It's possible to replace phosphorus by silicon and some other elements as well. But phosphorus compounds are the most stable. There are other oxidation numbers than +6 for molybdenum and tungsten, all the way to +2, +3. They are interesting, but they are less stable on air. Next, group number 7, rhenium perrhenate, very similar to permanganate, so oxidation number +7. When permanganate is relatively exotic for manganese, ammonium perrhenate is the most available compound for rhenium. You can reduce it with hydrogen to make rhenium metal. You can simply heat it in order to have rhenium dioxide, similar to manganese dioxide. You can make oxide E2O7. Rhenium complexes, as we have seen before, tend to have polymeric nature. Technetium doesn't exist in nature. It's a radioactive element, it's a synthetic element, has compositions similar to rhenium, and has several medical uses of interest.